So we're doing FID today, free induction decay. And so this is basically a continuation of the previous two lectures. And so what did we do, in 2 lectures ago? It was a signal equation. And that one was, we tried to write a simple equation for like what the signal is that comes out of the coil. And so, we had, so the signal equation, we had, precessing nuclei, and then they induce a voltage, and then we said there's this phase-sensitive detection, which we didn't explain yet, but if we assume that, then we can get this complex number at each point in time. So that was the signal equation one. And then we did phase-sensitive detection. How do you actually make 2 numbers out of one, a stream of, 2 streams of numbers out of 1 stream of numbers? And that was, you take this voltage and then you run it through this multiply by the transmitter frequency. And so today what we want to do is these equations were like extremely simplified, assuming there was only one frequency, but there's not just one frequency. And so what happens if we sort of extend out to allowing for the fact that there's going to be multiple frequencies at the same time across the whole head? And so that's what we want to talk about today. And so, multiple freaks. So, and this will introduce the idea of T2 star, because T2 star has, and so what is T2 star? T2 star is the kind of contrast that we use for almost all functional MRI. It's caused by changes in the oxygenation of the blood, which affects the magnetic field. And so pretty much like, at this point, like 80% of the scans done at the MRI center are T2 star weighted scans in order to monitor brain activity. So what's the star? So today is like, what is the star in T2? Where does that come from? And when we go through the equations, I'm only going to go basically through one equation, but you'll see that the kind of style where we mess around with the equations, a lot of times what happens is you write down a general equation, but it's kind of useless because it explains everything in a sense, but it's got parts that are sort of unknown, like what is the distribution of frequencies, which is what we're going to talk about today. And the way you work with this is you say, well, what if we had, let's just make up a distribution that sort of looks like a real distribution, but it's better behaved, and that's basically the strategy. So if we allow for multiple frequencies, then our signal, we'll have to write an equation that will, for our complex valued signal over time, that allows there to be more than one frequency. And so what we want to do, so that one is a function of time. What we want to do is integrate over all the different frequencies. And to start with, the very first thing we have in there is sine of the flip angle. And so, where does that come from? So why does the signal depend on the sine of the flip angle? And so the idea there is that if you start off with a certain amount of longitudinal magnetization. So this is, magnetization longitudinal. We often use that instead of the z direction. So longitudinal, sort of down the length of the bore. And if we do some kind of flip of that magnetization, if we went all the way down to the x-axis, the xy plane, that would be zero magnetization longitudinal, because it would go all the way down here, and then if you went all the way down there, we would essentially have no z component. But you don't have to necessarily do that. So what if we went down to, say, about here? And so now, how do you calculate the z component? Well, what we want is we want that amount right there. And what is that amount? If this is the flip angle, then that amount is going to be the sine of the flip angle, because it's the sorry, not that amount. That's what we can't record. Remember, I told you can't record that. So what we actually want is the amount of transverse magnetization. So we want this amount. So that guy is the magnetization transverse. That's the only one that we can record. And so let's get rid of that there. Okay, so what is that? What is that length? That length is basically the sine of that alpha angle, because it's the opposite. The sine is the opposite side of the right triangle. Here's the right triangle right here. So that's where the sine. So you see a lot of sines, and that's in the homework you have to sort of calculate how much longitudinal magnetization as opposed to transverse magnetization there is for one of the problems, and that's how you would do it. So that's the first thing that just scales everything. And then what we want to do is sum across all, so integrate the following thing across all frequencies. So this is, so frequency, across both negative and positive frequencies. So you can have negative frequencies as well as positive frequencies, and we'll talk about that a lot more when we talk about the Fourier transform. So for a point in time, let's sum across all the different frequencies that are in the sample. And so what are those frequencies? Well, there's this function, another Greek letter rho there, and that's the distribution of frequencies. So this is the spectral density function. So that just means like how much of each frequency is there. So, a given frequency, there'll be 0.2, another one there'll be 0.01. And then we have to consider the decay, because this is a time-dependent thing here, and so now we're actually considering the decay, because we're talking about times in the 10th of a second range. And so then we have e to the minus t over t2, but that one is going to also be a function of frequency, because different we're going to have sort of different T2s for different frequencies, because once we sort of expand out to multiple frequencies, then we have to consider the fact that the T2 number is going to be different for different frequencies. You'll see we throw most of this away, but we just want to write out sort of the equation that sort of describes things accurately, and then we'll sort of muck around with it to try to make it simpler. And then, so that guy was the decay, starts at 1, falls off. So this is, time dependent T2 decay. And then we have the oscillations, and those will be different for each different frequency. So these, so there's the frequency variable again, and then time is there too. And then the whole thing is multiplied by sort of a small little range of frequencies. So basically this is just the way you would just straightforwardly, you would just sum, you figure out how much of each frequency do you have, you decay it by, in possibly a frequency dependent fashion, and then you figure out, this one, remember, is the rapid oscillations. So, rapid precession, that's amplitude equals 1. Complex number amplitude equals 1. And then you figure out essentially what direction the vector is pointing, and then you add that to the whole sum across all the different frequencies, and then that tells you for one time point what you should get, taking into consideration there's all these different frequencies in there. So when you look at this, you say like, oh, okay, that's great, but what's that? That's just an unknown. We don't know what the distribution of frequencies is. And how could we possibly measure the distribution of frequencies? So the strategy here is, let's just assume that the distribution of frequencies has a particular shape to it. And why do we do this? There's theoretical reasons for doing this, so we could go, there's a whole sort of background of how people came up with this, but basically if you make certain assumptions that all the particles that are generating these frequencies are all sort of doing the same thing to each other, you can come up with a simple distribution, and we'll just say like, okay, well, let's just assume we had that distribution. Is it like a real one? Yes, it actually looks quite a bit like the real. If you try to measure the range of frequencies that you get out of a sample, you get a distribution that looks quite a bit like this. It's not exactly this, but it looks quite a bit like it. And so what is that? What is that equation? And before I go forward, whenever you have like an equation like this that has a number of parts in it, if you're like me and you didn't really study any math and physics, and you're reading papers and you text, equation, text, that's no good. You're supposed to go like text, then you look at the equation and you go like, this guy, okay, like where is that? Okay, is that over there? No, this one's over here. So, it's important to, look at the time here. So, the time is here also, and it's also here. But it's not in this guy. And then what are you integrating across? So here, you're integrating across frequency. And so here's frequency there, and then you got frequency up there, and you got frequency here. We'll eventually throw that away. And it's also up there, and then that's here the thing, the increment of frequency. So when you look at the equation, sort of make all those connections so that we know exactly sort of how the machine is working. So this, for one point in time, which is over here also, we integrate all these, over all these frequencies. Okay, so now let's just assume that we got some kind of distribution. So let's assume that this thing looks like the following. And so we'll have an MZ0 in there, and then we'll have that thing. And so what is that thing? So that looks like our very first equation. Remember, our first equation was the resonant frequency is equal to the gyromagnetic ratio times the B field. So this thing is a frequency, or it's a frequency difference, because what that delta B0 is essentially sort of a number that says how wide is the band of frequencies that we're considering. So that thing is like that thing is like a frequency, which is, and we're squaring it, and then we're dividing by the same thing down here again. So that thing squared. So those things are constants. Those are they're just a lever that will tell us like how big the range of frequencies that this spectral density function is going to give us. And then there's still no, those are just constants, and so then we finally have the variable in there, and so the variable is there's the frequency variable, and it's subtracted off from another constant, which is the center frequency, and that thing is squared. So what does this equation say? This equation allows you to set a center frequency and then have a distribution of frequencies around it. So that's why you're subtracting off the center frequency. That will have the effect of subtracting off the center frequency will have the effect of moving this curve to center it around the center frequency instead of being centered around 0. So when you see an equation like this, just stick it into MATLAB and just, fiddle with it a little bit. So, how would you do that? Well, what is the equation? Well, the equation is like y equals, some constant over another constant, plus a variable. And so, call that guy x, and then just plot that. Set up that equation in MATLAB and plot it and just see what it does. And, what does it do? Well, it will make something that sort of looks like a Gaussian. So it will be centered, if we just do this one, without subtracting off the center frequency, that just sort of simplified a little bit, you'll get something that will go up to 1. So why does it go up to 1? Well, just, stick in some constant there, like, for instance, 1, and then look at, if this is x going in that direction, you're going to end up with, x equals 0. So at x equals 0, what is it going to look like? Well, it's just going to be, if that constant was 1 or whatever it was, it's just going to be constant divided by constant is 1, so it's going to be 1. So if you then plot out the equation, what do you get? You get something it sort of looks like a Gaussian. It falls off a little different than a Gaussian, but it's something that looks like that. Goes up to 1. And then you can say, well, what happens if we fiddle with the constant? Well, if you fiddle with the constant, if you make the constant bigger, it will still end up, peaking at 1, but it will, it will generally multiply the curve by something out here, so you'll get a curve that looks something like this instead. So this is, this would be, c equals 1, and this would be c bigger than 1. And so it's going to be a distribution, sort of symmetrical distribution of frequencies. In this case, for this very simple equation, it would just be around 0. But since we subtracted off the center frequency, it's going to shift that curve somewhere around wherever the center frequency is. And what's the reason for this? The reason for this is we want to try to estimate something that actually does happen in real life. And if you actually just take a sample, zap it with an RF, and record the range of frequencies that come back, you get something that looks like that. And depending on, how well you've shimmed things to sort of flatten the field again, it will be sort of, bigger or narrower. Okay, so when we look at this one, now what is that thing going to be? That one's going to be basically the, for this one, just think of our original equation, which was the resonant frequency equals the gyromagnetic ratio times the B0 field. And so this thing will basically make something that goes up to MZ0. And then the width will be, so this thing will now be centered around whatever the center frequency is. And then this curve that you get, this will go up to MZ0 because they're multiplying by MZ0. And the width of that is going to be, proportional to this range of frequencies. So this knob allows us to adjust the width of this, and it goes up, instead of going up to 1, it's been multiplied by MZ0. So now now that we've just stuck in this made up distribution of frequencies, which sort of looks like our real frequencies, now we can actually sort of, operate this equation. And so the first thing we could do is, instead of assuming there's a whole range of frequency, what if we just solve for just having one frequency? And so you could just use this equation for one frequency, you'll basically end up with our signal, our signal over time is just equal to what we had before. And so what we had before was, however much starting magnetization we had, and then we multiply it by the sine of the flip angle, because it just depends on how much transverse magnetization we're getting, because that's we can only record the transverse, we can't detect that Z component. And then it will be decayed by, however long we are out on the T2 decay curve, and then to try to figure out what the instantaneous, angle is, we'll have this, minus I, whatever frequency we're considering, times T. And so that's exactly the same as our original signal equation, or the equation that we had in the, this is basically just the amplitude, our starting amplitude of the signal. Okay, but we don't care about that. So that's if you integrate this equation with just one frequency. But now we want to, that's what we already knew, but now let's integrate it with multiple frequencies. And we won't go through the whole, we'll just write out the answer, but basically we want to substitute this thing into here, and then rearrange the equation to kind of peel out the center frequency, and then take the integral. And so let's just write down the answer. So the answer is, it starts off with pi. So where does pi come from? That's the first thing I said, when I looked at this. Well, if you integrate something like this, you end up with a pi. So you can try to sort of, integrate something like this and convince yourself that you're going to get a pi out of there. So there'll be pi times the that constant there, times the, sorry, I'm just going to give myself a little bit more room to write on top of the equation to describe different parts. So here, let's start again, a little lower. So here's our signal. So it's equal to pi times the starting longitudinal equilibrium magnetization, because we're assuming that we went in there for a couple seconds, got magnetized, and then times however much we flipped, sine of however much we flipped. And then we're going to have one decay term that includes this width of the frequency band. So that's gamma times delta B0. That's all one thing. So I wrote them all close together. Now, when you look at that, you go like, well, how come it's not in the denominator if it's some kind of time constant? So it's kind of the inverse of a T2. So let's put the regular T2 one in here. So we're going to have the regular T2 minus T over T2. And how does that one work? That one works as you lengthen, as you sort of make the T2 bigger when it's in the denominator, it has the effect of making a shallower drop-off. So, and that makes sense. So larger T2 being in the denominator causes this thing to drop off more slowly. But this thing is in the numerator. And so if it's in the numerator, then what's going to happen is if you make this one larger, if you make the delta B0 larger, it's going to drop off more quickly. So sometimes what people write instead is we just call this thing, this whole thing, a time constant. So let's change this into 1 over T2 prime. So it's another kind of a T2 thingy due to the width of the frequency band. And the way it works is wider frequency band, faster drop off. And then finally, we have the oscillation. So here's the oscillation, minus I. But notice, now we've got a constant here. So we've got so that guy's that's a constant. So that's this guy right here. Oh, sorry, wrong guy. It's this guy right here. It's a constant. It's just the center frequency. So that's kind of weird. So what this says is that if you mix together a whole bunch of frequencies that have this kind of a distribution, this thing is called a Lorentzian distribution. Lorentzian distribution. It has the convenient property that it's actually equal to one frequency. You just get a single frequency out, just like our original equation. Now, of course, in real life, you won't have exactly that distribution. You should probably get a couple frequencies mixed together. But you can describe the output after you do this, after we basically take this guy, substitute it in for that one, do the integration. This is what we end up with. Amazingly, just one frequency. So let's just annotate all these guys. So this is this guy is from integral of constant over something that looks like that. This guy is just equilibrium. How much magnetization do we start with? This is, the flip dependence. This guy is, let's start off with this guy. This guy is just the time dependent because we need time over here. Time-dependent T2 decay. We'll say what's causing that. But this is additional decay. Additional time-dependent. So due to width of the frequencies. So the wider the frequency, the way this one works, the wider the frequency band that we assume, the more time-dependent decay we have. So as you widen the range of frequencies, you still end up with just a single frequency coming out of here. So this is basically just a single frequency here. This is the precession. The rapid precession, but single frequency. So we just get like one rapid precession single frequency coming out with two decays in it. This regular T2 decay, which we'll try to explain like what causes the regular T2 decay, and then this additional component. And usually what people do, because it's a little difficult to directly measure that guy, is they glom these two terms together here, the extra decay and then the T2 decay. And mathematically, how do we do that? Well, if you multiply two things that are, that have exponents and the base of it is the same, the E is the same, you can just add the exponents and turn it into a single thing. And so basically, that's where we get T2 star. So T2 star, just equals those two exponents added together. This one, the one over to the T2 prime, which was this extra decay term, which we turned into a time constant by putting it in the denominator, plus the regular T2. So that's what the T2 star is. And so so the typical way that you finally write out the equation is to glom those two decay terms into a single one. And so you get, pi times whatever the equilibrium magnetization times the flip dependence times just a single decay term minus T over T2 star times the rapid oscillations that are at the center frequency. So that's our, so here's the whole thing, and here's the one, so the more typical one. So now we need to sort of say what are the two different decay terms coming from. So the first one, so the regular T2 one, this one is called intrinsic decay. And so what's causing the sort of, from a physics point of view, what's causing this T2 decay? So what's causing the T2 decay is, just put yourself down in the position of a single proton. So a single proton is precessing around, and as it precesses around, the magnetic field of that proton is wafting around in space. And there's another proton right next to it, and that one's also precessing around, but maybe it's got slightly different atoms around it, or maybe it just got hit by another atom, whatever. What's going to happen is it might get slightly out of sync for whatever reason, just because maybe it's next to an oxygen atom or whatever. And so what's going to happen is its magnetic field will be slightly different and get out of sync with the one right next to it. And so what will happen over time is there's all this sort of, rapid jostling. So there's all this rapid jostling that's happening from all the atoms that are around. And that kind of decay is unrecoverable. And we'll see, because it turns out we can recover other kinds of decay. Unrecoverable. So that's going to happen no matter what, the T2 decay. So it's this intrinsic decay just due to the fact that the magnetic fields that the protons are oscillating around in are all themselves rapidly oscillating, slightly out of sync, or just depends on exactly where the atoms are relative in this particular biomolecule. And so that's the true sort of like unrecoverable, very high frequency, because we're talking 123 million oscillations per second kind of decay. So that's the first part. But what about this T2 prime, not T2 star? It's like the T2 star equals the T2 prime plus the T2, which is the only thing that we can directly record. So this guy is static. So this is a static decay just caused by very slowly changing local magnetic field. And what do you mean like slowly changing? That means like, something that's down in the range of a second instead of 123 millionths of a second. So turns out this one is recoverable. It's possible to fix this. So this guy, and we'll talk like just on Friday about spin echo, which is a way of kind of recovering this one. So what are these? If we could somehow sort of potentially separate out these kind of things, what do they look like? So let me just before I talk about that, let's just draw out sort of examples of this equation. So this equation is, it's the same one that we've been dealing with the whole time, but let's just assume we have some frequency distribution that is a Lorentzian distribution. So it's one of these ones that looks like this. It's kind of centered around, our center frequency here. And what happens if we run that equation? Well, we get gazillion oscillations like that, and that fall off there is going to be equal to e to the minus t over T2 star, because we sort of combined those two things in there. Now, what if we don't have something that's actually a Lorentzian distribution? So let's just take another example, like what if we solve this equation, for instance, with something like this? What if we just have like a band of frequencies? So here's the omega 0 down here. That's not a Lorentzian distribution. And what we get from that is something that's a little different. It might look something like this. If I just sort of draw the envelope of it. So there'll be some oscillations, and then they'll go down, and then they'll go back up again, and then they'll go down, and they go back up again, down. And if you've got a sample in the magnet or a human, and you're trying to shim, you could see something like that. So it won't be e to the minus t over T2 star, but if you actually calculate you can get something, you know, that's pretty close. It'll be sort of about the same as e to the minus t over t2 star. It won't be exactly, and so this is because the distribution is never exactly this distribution. So but when we look at the signals that we actually get out of the magnet, which is always T2 star, because there's always going to be some static field offsets. What is the sort of basic relationship between how strong those signals are? So it turns out that T2 star decay is a lot more rapid than T2 decay. So a typical kind of decay curve that you get for T2 star might be something like this. And what would that look like compared to T2? T2 is going to be something more like about like that. So this is a big effect. So this guy is, you know, e to the minus t over t2, whereas, you know, this guy is e to the minus t over t2 star. So there's a huge amount of decay from this fact that there's some quote-unquote static, not exactly static, but, you know, static compared to this like super high frequency ones, in homogeneity in the magnetic field. And this occurs even just like if you've got a little sample of, like, you know, some table salt or something like that. The same thing will occur even with something like a little tube of salt water. So this is the only actual signal that we can directly record. We can do various tricks to recover, sort of temporarily at an instant in time, recover the signal by sort of using a gradient or using another RF pulse to sort of flip things around so that the guys who are ahead are now behind, and so you can sort of cancel out the delays. Basically, that's what a spin echo is. We'll talk about it in detail. And then you can sort of like recover this temporarily for an instant in time, recover the signal that was killed by the fact that there was this distribution of frequencies, right here. But in general, we can only basically record the T2 star, because that's the signal that we can basically record. And what are we interested in doing? We're not interested in just recording the T2 star or the T2. What we're interested in is contrast. And so what we really want to know is, like, you know, here's another thing. So this is another kind of tissue with a different T2 star. And so and that would, for instance, be something that, say, deoxyhemoglobin, which basically sort of disturbs the magnetic field. And so deoxyhemoglobin is going to slightly kill your signal. So what you're really interested in MRI isn't really just the decay curve per se, but we're interested in is, like, here's another tissue type and it's decaying at a slightly different rate. And it might have a different T2 value. And here's another tissue type, or maybe an activated part of the brain that's decaying at a different rate. So we're always interested in the contrast between, like, two different versions. So that's actually what all the action is about. Like, you know, trying to figure out what that contrast is. You know, contrast, you know, between, you know, different, you know, tissue types, but or activated versus unactivated. And so what we'll talk about over the next week is how do we maximize, how do we find a way to maximize the difference between these two different tissue types that are decaying at different rates. And it could be either the T2 part or the T2 star part. For fMRI, it's all about the T2 star part. So that's the main plan. So the plan was, isn't it unrealistic to assume that you've got just one frequency? And the answer is yes. Okay, so here's a general equation that describes how to calculate what the signal is going to be for any old frequencies, any old distribution of frequencies. We just assume that we've got this simple to deal with kind of distribution of Lorentzian distribution of frequencies, and which it has an adjustable width. So the delta B0 tells you how wide it is. Now notice one thing that's a little confusing here. Where did I put that? Yeah, as you increase the range of frequencies, you're going to. Did I leave something out? Oh yes, I knew I left something out. Okay, sorry guys. My final point. We left out. We've got the another constant in there. We've got this guy in there. I should look at my notes. I'll always look at my notes, and that one's down here too. So the width of the distribution is in there. Sorry guys. Okay, I can see I left it out last year. I was looking at my last year notes. Okay, so you might wonder, why is that guy in there? Why is that guy in there? And so what that means is that as you turn up the width of the distribution, so if you turn up the width of the distribution, this guy is, the width of frequency dist. The signal gets bigger. And that's a little counterintuitive. Like, why does the signal, why does the signal get bigger when you turn up the width? And the reason is you've basically got more frequencies in there. And it's also just the way that this Lorentzian distribution behaves, because you've just got more area under the curve as you make the curve wider, because the curve is clamped at a single maximum. And so that's why this sort of counterintuitive term is in there. So like for a wider range of frequencies, you're going to end up with a larger amplitude signal. But it's just because of the way Lorentzian distribution works, that it's got a maximum. And so as you add more frequencies in there, you're effectively sort of adding just more signal. And so it's just directly proportional to the width. So it's good that I didn't leave that out this year. So, but just to sort of go back to where the overall summary. So the overall summary is we assume this simple distribution. When we integrate across, stick this thing in there and integrate, what we end up with is a second decay term. And the second decay term is proportional to the width in such a way that the wider the distribution is, the more rapid the decay. And then we've got the regular decay. This is our regular intrinsic decay, and then we have the rapid oscillations. But the rapid oscillations all boil down into a single frequency. So our signal just comes out as just one pure frequency, even though what's actually being added together to make it is a whole bunch of different frequencies. And then basically for the most part, we just glom these two guys together into one T2 star term. which is the only raw signal that we can record. And we can do little tricks to, at an instant in time, try to estimate what the T2 is. But basically, T2 star is our free induction decay, which is just, what that means is the free decay of signal after we stimulated some signal, but then didn't do anything else. That's the free part. The free part means we hammered it, and then we stopped hammering it, and then we just recorded it and allowed it to do whatever it does. And if you read MRI literature, they'll use FID just to mean signal. You say like NFID, it just means like we did something and here's a signal. Okay, so any questions in the last negative 4 minutes about, yeah? Oh, to get wider? So what sort of actually controls this sort of like range of frequencies? Strictly just the local strength of some magnetic field offset. So say you have, a simple thing is like you turn on a gradient. If you turn on a gradient, then all the different parts of the sample are going to be at different magnetic field strengths. But in practice, it might be something like this. It might be like, here's your nose, here's your brain. There's some air in the nose right here, which is pretty close to the brain. And because this part of the brain has a lot of protons in it, it's pretty magnetizable, and the air isn't, it's going to cause a gradient in the magnetic field there. And so then that's going to actually cause a larger range of resonant frequencies around this part. And so lots of different things can cause this. The oxygenation in the blood can cause it, because some part of the blood can become strongly magnetized because you've got a lot of iron in there, and it's possible to magnetize the blood, and that can cause like a change in the local magnetic field across space, near a blood vessel, and then that's going to increase the bandwidth of different resonant frequencies that you get around that blood vessel. So many different things. Anything that disturbs the local magnetic field is going to cause that. From the exact sort of like B0 strength, and there always will be stuff. One thing that causes it is, turns out some brands of dry shampoo, for whatever reason, I don't know if they put metal in it or something, but we were scanning somebody that had put some dry shampoo in, and there was this huge dent in the head. We said, like, what? What's that? And we said, we know, we put them in there. We didn't see any large dent in the head when you put them in there. I know they're probably okay. And so it turns out that some component of the dry shampoo was causing a massive disturbance in the flatness of the magnetic field, and completely messing up the signal. So we added that to our screening form. Have you used any dry shampoo recently? Okay, I think I went over enough, so we'll see you guys on Friday.